Welcome back, everyone. The next talk, the next two talks are sort of the more quantum-y version of the event. Next up is Tom Mainiero, who, if you haven't read his abstract, I should. In there, he's inviting us all to spice up our entropic life with higher entropy.
Thanks for inviting me here. This is awesome. My brain sort of exploded on Wednesday with a bunch of ideas. Thanks for organizing this, to all the organizers. John and Goen is the name. Yeah. So this is great. I've had a lot of fun. And now that you've all well fed and very sleepy, hopefully I can remember any of the jokes. I probably don't remember any of the jokes I came up with, so I apologize in advance. Maybe I'll do a dance or something in the middle to wake you up. So this is a very schematic talk, especially because it's a Blackboard talk. I never really get to write anything down in detail, but if you're very interested in the details, and there are quite a few, you can check out my paper, Homological Tools for the Quantum Mechanic. It's on the archive. If you want a short version of the things I'm saying here with a bunch of sophisticated terminology, you can also check out my String Math 2020 talk. I say some details that I really don't mention here. And in the future, I'm going to use this to promote, and I know, again, you should not promote future work apparently, but 90% of this project is already done. I have some work going on with Roman Gayko, who's in the audience here, and Greg Moore, which is describing this really beautiful equivalence of a bunch of two categories. And that's somewhat related to the things I'm about to say today. So hopefully you won't understand this diagram, but you'll be very impressed by it, maybe by the end, and get a feel for what the heck is going on here. And so maybe I'll mention some more words about that later. Okay, so I have this title, this talk, Higher Entropy. So what the heck do I mean by that?
Tom?
Yeah.
Might you be able to write a bit bigger for us Zoom folk?
Yeah, I'm gonna end up writing smaller just because I know habits. So just keep like yelling at me or something. This is not big enough. I'll just.
That's great, thank you.
Okay, so I can think of this as sort of, well, higher entropy at the sort of easy level, I can think of as, the categorification of entropy. And I can think of this as sort of taking the question, how much ignorance do I have? And I ask myself this every morning because I have low self-esteem. And I can try lifting that to the question, what is it that I don't know? And my parents try to answer this question quite often. So let me try to make this more precise. In particular, I want to take something like, can people see below here? Okay, can you see all the way to the bottom?
Yes, I think so, but
okay,
not the top.
Yeah. So I want to take relative entropy. So if you don't care about relative entropy, entropy is just fine. All entropies are really relative. And I want to lift that to something like a linear space or vector space. And what does this vector space consist of? It consists of random variables. And the thing is, by measuring these random variables, I will reduce my ignorance and become enlightened. So that's the vague interpretation here. So in particular, because I don't want to go on the bottom here, I'm unfortunately going to erase this.
We can see the bottom. Yes, we can see the bottom.
Yeah. I'll lay down on the floor and it'll be very interesting. No. So for example, if I start it with a state on a finite set, or measure, sorry, people don't know where the state yet. Omega here is a finite set, and mu is just some function on that. This is a non-normalized probability measure, just known as a measure. I can compute, its Shannon entropy. And I'm going to put hats on things just to be consistent with later in my talk. And I want to lift this to the space of functions on omega where mu is non-zero. So what the heck is this LQ? If you don't know what an LP space is or an LQ space, don't worry. Just think of this as the space of complex valued functions on omega. And the Q here is sort of a parameter that describes a possible norm you can put on this space. So the LQ norm. Okay. So and there's this magical thing. The Q will pop up later in the talk, and that's why I'm mentioning this now. And Q you can actually think of as a complex number and for finite things. And in general, it lives in some weird upper half plane where real value of Q is greater than 1. And this is related to some beautiful modular theory or sorts of very cool things that I won't really mention, but it's just cool to keep in mind. Okay. So that is the one categorical sort of interpretation of things. Now, if you're a fancy pants homotopy theorist, you might think of higher things as something different. So usually you think of like graded objects or chain complexes or something like that. And I'm going to erase stuff because I don't have much room. And yeah, I'm just going to think of that question as, right, how much, so the homotopicals perspective of this question, and I'm not going to discuss much about this. This is sort of the theme of the homological tools paper. It's the question about how much info is shared. And I want to lift that to the question of, what info is shared. And similarly, here, instead of lifting relative entropy, I'm going to lift mutual information. So I can think of this as if I have a measure. Oh, yeah, let me lift mutual information to something interesting first before I write down what it is. I'm going to lift it to something like a space. And I don't mean like vector space here. I mean something vaguely like a topological space, right? And the manifestation of this is something like a chain complex or a simplicial object in some category, or even just a simplicial complex, it turns out. Okay. And so, right, so what is this in terms of, actual concrete symbols? Well, what does it mean? In order to ask this question about how much info is shared between people, I'm not just talking about a measure now on a single set. I'm talking about a measure on a product of sets. So think of some omega A, omega B. And then I can talk about the entropies of the subcomponents of these things. And I won't write out explicitly what that means. You just take the reduced measures or the marginal measures, or if you're a quantum mechanical sort of person, the partial traces. And it's just the sum of the entropies on the components minus entropy on the total thing. Okay. And that's going to lift to something that looks like a space. And sort of abstractly, what this means is that I have these two reduced measures. And you can think of this thing as forming some sort of complex. So if you are familiar with CW complexes or simplicial complexes, you can think of these as 1 cells and these guys as 0 cells. and I'm gluing the 1 cells together along these 0 cells. Okay, and this is a very concrete expression in some category of measures. And the idea is that this alternating sum, believe it or not, arises as something like the Euler characteristic of this complex. So okay. So now I come to the big fancy diagram. How much time am I in? Okay, good. All right. So you're not going to understand anything that's going on here. Again, this is just to impress you, make me feel better about myself that I said something good. You can start out with some multipartite measure, and I'm also going to use the word state for measure. And that just means like a measure on a product of sets, multipartite. Yeah.
I just need to clarify, when you say what info is shared, the info in that question is referring to the measures, correct?
The info is referring to like correlations between random variables in the measure. Yeah.
Okay.
Yeah. So this is like measuring correlations. Yeah. And explicitly, you're realizing the random variables that exhibit those correlations explicitly. So the correlations are measured numerical quantity on this side, and here you get actual random variables that are correlated in some maximal way. Yeah. So that's what this homological thing does. The homology produces tuples of random variables that are maximally correlated in some very precise way. Yeah. So yeah, the big picture is that I start out with some multipartite state. I produce this fancy simplicial looking thing, and that's hard to think about. So what do you do when you have a hard to think about space? You abelianize it. You think of like something simpler. You probe it with something easier. So that's what this homology does, homological construction. So you take its homology, and you get some graded vector space, and sort of the kth component of that space are like correlated random variables. Sorry, I'm writing maybe writing too small here, but I don't have much room. That you can only see that are correlated among k subsystems, but no smaller. So you can only sort of detect these correlations by looking at k parties at once. And actually, there's a stupid degree issue here. Okay. Okay. So enough about that, though. This is a thing you can read about in my homological tools paper. In particular, I suggest you read the introduction because it's a long paper. That should be enough. And that's too complicated maybe for you. So maybe I just want to take the Euler characteristic, which is an alternating sums of the dimensions of this thing. That's a bit easier. And if I have graded vector spaces, I just end up with an integer, right? Well, that's interesting. I'm getting an integer somehow out of these measures. So what the heck does that mean? Well, it turns out that you can actually think of this integer as the limit of some deformation of mutual information, which is related to Solis information. And actually, in the quantum case, it's related to Solis and Rainey. And that thing you can derive just by thinking about what is the dimension of an object in the space of states, in the category of states, excuse me. Okay, so, and on one hand, when you take this parameter q goes to 0, it's like the L0 space, which is a funny thing. You get this integer. And on the other hand, if I take the derivative at q equals 1, I recover standard mutual information. So this whole picture actually just works for a unipartite state. So it's, when I think of unipartite, just on one system, no products. And just to entertain yourself, if you're getting bored, you can take the word unipartite. I freely associated that with the word unitard, and so you can think of your states all dressed up in unitards and dancing around if you want. So that's my irreverent joke. So yeah, so there's this, yeah, again, this, entropy is arising now as some sort of derivative, again. So we've seen this sort of theme throughout these talks. Okay. All right, so, all right. Yeah, so you might ask, why should I even be thinking about this? Why is this possible? I will just say the first point in words because I give a good description of it in the introduction of this homological tools paper. The first reason is whenever you think of like correlations among like disjoint subsystems, I think of like global things and obstruction. Obstruction is something. And whenever you hear those words, like, or your homological alarm bell should be ringing in your head. And you could actually make this point very precise. And just from that thought, you can reduce down to computing the cohomology of a measure or of a state. Okay. On the other hand, you look at this alternating sum of mutual information, right? And you say, oh, I know other alternating sums, right? The Euler characteristic of a space. So if I take, a space and I separate it into a union of subspaces, right? It reduces down to the Euler characteristic of the subspaces minus the Euler characteristic of the intersection. Or even more simply, if this were a simplicial complex, then it's just an alternating sums of the number of cells, that generate that thing. And this alternating sum, however, is just like an Euler characteristic, only depends upon the number of things in that space, right? It doesn't tell you anything about the gluing. So, and that's good because it's easy to compute, but it's also bad because you're losing a lot of information. Yeah, so there are instances where, yeah, so this I, what I'm saying is that this I should look like the dimension of, and when I say dimension, I mean a generalized form. So Euler characteristic also means a dimension. So look like this. And now this is not quite right, it turns out. Again, it's a derivative of this whole family of dimensions that depend upon a parameter q, but this is a good enough intuition. So this thing sort of measures the information shared among subsystems. And if you generalize mutual information to higher and 3-part type, 5-part type systems, what you find is that, this guy, the generalized version of it, it measures mutual information. That's what MI will abbreviate. Measures the info shared among all subsystems. And the way to see that is if you have I of the tensor product of measures, which I can just think of as the measure on the product set. So I'm using this, you'll see in a moment for why I'm using this tensor product. This is 0. So on the other hand, if this vanishes, you can ask the question, does my measure split, right? Can I think of my subsystems as all independent? That's what this is saying. Turns out no for 3-part type things. So the implication doesn't go the other way. Mutual information vanishing doesn't necessarily mean that your state is things going to factorize. So this is a reason for cohomology. It's just like when you have a 3-manifold, compact 3-manifold, and you compute its Euler characteristic, it vanishes regardless of what 3-manifold is. It tells nothing about the gluing information. But the cohomology tells you something interesting. And there's examples for which this is true in the quantum mechanical case, at least. Okay, so that was just pitching the whole cohomological thing. And how much time do I have left? Okay, good. Yeah, just making sure I'm on track. Yeah, so now that I've, maybe hopefully the food coma is wearing off, and I can start telling you something about what the category of measures actually is, right? What is this category I'm computing stuff in? And there are relations to a lot of things we discussed in the past few talks. I can't really talk about them because, you know, I don't have any concrete things to say quite yet, but yeah. Yeah, so sorry if I have poor board work. I, you know, didn't get to practice on this board. Try to write bigger again. Okay, so from now on the talk, I might use the word state instead of measure. And that's this language I'm actually deriving from the C-star algebraic world. It also helps you think about, if you know anything about quantum mechanics, the quantum mechanical version of everything here. So my talk is not just about quantum mechanics. And this whole paper, believe it or not, I engineered it to make physicists interested and talk about purely about quantum mechanics. You could translate almost everything there into just pure measure stuff. And by the way, I should also mention that these spaces I'm talking about, these abstract spaces, become concrete simplicial complexes for the measure case. And I can give like 2 talks about that, but I decided to go with the crazy abstract stuff instead, unfortunately. So just as an example, if I have like a measure on 2 sets concentrated along the diagonal, you get a nice looking space here. And I can take the cohomology of that, and that tells me about random variables on that thing. So you might have seen pictures like that. I think Ty Dene on her blog has written nice pictures like about those things. And you can generalize this to higher partite things with, you know, higher simplicial complexes. Okay, so that out of the way. What the heck is this thing? So what is a state, right? Let me give some good definition at least. A state is a pair of a star algebra. And so what I really secretly mean is something called a W star algebra or von Neumann algebra. But I know a lot of folks don't like thinking about infinite dimensions. That's fine. You can live in the finite dimensional world and just think of star algebras, complex numbers, right? A, let's call it A. This A is different than this A. Sorry about that. And a positive linear map. Let's call it, I'm just going to stick with the notation mu. If I write down a row, I mean mu, just let me know, from A to C. Okay, so what the heck is this? This is like the expectation value function on the space of random variables. So A is like the space of random variables. And this is the expectation function. Okay.
You want some normalization condition, or
No normalization.
Okay, cool.
Yeah.
So we don't
that's actually quite important for what I'm going to do. I have the philosophy that you should only impose the normalization at the end, or look at things that are invariant under rescaling.
I like that. Okay.
Yeah.
So in particular, mu of the unit doesn't have to be 1.
It doesn't have to be what? Right. It doesn't have to be 1. Yeah. It should be finite though, if you think about infinite dimensional stuff. Yeah. So no like Lebesgue measure, but there's ways of dealing with that. Yeah, and so positive just means that this thing on A star A has to be greater or equal to 0. Yeah, so the big example that you should keep in mind that takes into account both the classical and the quantum case is A should be the product of matrix algebras. So when I write product, some people call this the direct sum, but it's actually a product in the category of algebras. So I use this notation. Physicists get angry at me for doing that, but yeah. So what the heck is this algebra, right? Oh yeah, and so here, let me just write down what mu is in general. Any mu on this thing, any positive map, can be written in the following form. I can take my A. Sorry. And I can write it as the trace over the ith component with respect to some positive semi-definite thing. Okay. All right, so what's going on here? let's specialize. Let's think about the case when all the n sub I are 1. So all these matrix algebras are just copies of C, and A is isomorphic to C to the n, right? Well, in that case, C to the big N. In that case, what should my mu hat sub I be, right? They're positive semi-definite maps on M on C. What are those?
Negative numbers.
Non-negative numbers, yeah. So each of the mu hats of I are just non-negative numbers, yeah? And so you can think of mu hats as a function from the set 1 to n into positive real numbers. So at the other extreme, I can take big N to be 1, and then I just get one positive semi-definite map and one trace. And that's what's called a density state in physics. So it's, if you don't know what a density state is, just think of, but you know what a pure state is, a vector in a Hilbert space, just think of the projection operator onto that pure state. That's an example of a density state. Okay. So this example is what I want you to keep in mind. In fact, any finite dimensional C-star algebra, or star algebra, or C-star algebra, in fact, decomposes this way. So this accounts for all the finite dimensional stuff. All right. So now I want to define a category. And I've defined the objects, pairs of an algebra and a function on that thing. What about the morphisms? Well, it's easier first to fix the algebra and just look at morphisms that way. So let's do that. There's something. I hope it wasn't loud. To get the morphism, so let's look at so the definition is the category state A as objects. So here A is fixed, the algebra is fixed. Objects are states out of A, and the morphisms are given by the structure of a poset on this thing. So there's a unique morphism from U to V if nu is less than or equal. So it's the opposite, sort of opposite of the inclusion. There's a good formal reason for that. And so what do I mean by this? I just mean that mu of A star A is less than or equal to mu of A star A for all A. So this is where that positivity part comes into play. It's to define the notion of morphism on this thing. Okay, so this thing is actually, you think this is something really boring, but it's actually something really beautiful. Because if you think of these things as actual measures, for each one of these inequalities, you can say that nu is equal to some function times mu. So this is a real valued function, positive reals. And this is what's called the radon-Nikodym derivative. So there's a unique radon-Nikodym derivative associated to each one of these inequalities. This is really the real key behind a lot of things. Yeah, a lot of the structure has to do with this inequality.
Is there a reason why you're using this order as opposed to absolute continuity?
Yeah, this is right. You can also use absolute continuity in infinite dimensions. It becomes a thing where you have to deal with unbounded stuff. This has beautiful things where there's going to be this functor from the category of states into representations. And you're going to get bounded linear contractions if I take this. And as you might know, that bounded, short linear maps and bounded linear maps have nice categorical properties. That's why this is the best thing. If you want things up to a constant, you could also do that. But this is, this seems to have everything really cool right here. It also gives me the right notion of isomorphism class. Yeah. So what is, yeah, so if I want the algebra to vary, I'm not gonna tell you very much. If you know anything about Grothendieck op vibrations and all this sort of thing, what I want to do is I want to think of the big category of states as sort of fibered over the category of algebra. So if I choose an algebra A, I get some category of states. If I choose an algebra B, I get some category of states. Have some use of A in this fiber and some use of B. And I'm just going to draw a picture. I'm not really going to describe it. You can think of the category of states, state, as sort of the total space of this vibration. And what is a morphism here? Well, it comes from sort of a morphism on the bottom, which you could think of as a star homomorphism. Now, there's a beautiful generalization to things called completely positive maps, which are quantum versions of stochastic maps. But just for the moment, just throw star homomorphisms. And I will say that I have a morphism on the top in sort of the opposite direction if the pullback of this mu sub B is less than or equal to the mu sub A. So this gives you a one category. Okay. Now, you don't have to understand this, but don't think too hard because I'm not going to use this structure. But just know that once you have something like this, it all falls through and there's a nice category, everything where you can let the algebra vary freely. And this is precisely the category where you can construct these simplicial objects.
Speaking of contracting maps, would you be able to just write a bit bigger again? Sorry.
I can't hear. Oh, okay. Yeah, yeah. So can you? Yeah. Thank you for reminding me. I will try to write bigger in the future things. Yeah. That's going to keep happening just because. Well, that's the way things work in my brain. Okay, but thank you. All right, so yeah, other cool things is that you don't, instead of, you have, this category has these really beautiful properties. So state has coproducts. A, I'll write my coproducts like this, mu B. What the heck is this, right? Well, if I have two, this is the disjoint union of measures, right? If I have two measures on two sets, I take the disjoint union of those sets, then I have a measure on the disjoint union, right? So that's what my coproduct is. And I claim because I don't have any normalization on things, a lot of this operatic structure actually just becomes like rescaling. There's rescaling of things too. And you don't really see an operad so much as like things with involving coproducts and stuff, because you don't have to worry about taking convex linear combinations anymore. Yeah. So yeah, just algebraically, this is just the map from A cross B to C. I take a pair to the sum, right? You just write some things down. Then I also have a monoidal product. And so on the algebra level, the random variables on a cross product, the Cartesian product of sets is the tensor product of random variables. So that's what's going on here. And then, this is just the thing, A tensor B. This is just the thing that brings it to the independent, the factorized probability distribution. So a lot of things about deducing correlations is figuring out whether or not something factorizes with respect to this product. Okay, so that's great. All right, so now what's a dimension in this category, right? Well, there are many notions of dimension. The gold standard is the notion of a symmetric monoidal dimension, but that quite doesn't work for this category. There's not all the right structures yet. I'm looking at generalizations for which that might hold. So I'm just going to use a wonky sort of definition that's very powerful still, which is the dimension is just a homomorphism out of the rig of isomorphism classes. Or if you like Grothendieck groups, it's a homomorphism out of the Grothendieck group. So let me write that down. So if I have C, and I'm going to be vague about this, we can always nail down the details in discussions. C is a category. And I'll just say co-products for this one. With and tensor. Sorry, I'll write big again. Yeah, this is. Then I want the dimension to be a homomorphism out of iso classes of C into R, a ring. And it takes C1, I'll write my coproducts again with this plus sign, C2 to the sum. And of course, you want your coproducts and your tensor to interact nicely, of course. They'd have to distribute over one another for this to make sense. And then I want, of course, the dimension of the tensor product to go to the product. I'm writing things out. Yeah, multiplicativity of those. Great. So this stupid little notion, believe it or not, is quite a powerful idea.
Oh, quick question. Is it possible to consider this also to be like a functor if we consider the ring to be like a two-dimensional category or something?
Yeah. If you took like, I have a feeling that in my particular instance, you might want to like put some post-settle structure on here, and yeah, it's possible. I haven't quite thought about it very hard, but yeah, that would be very cool, and it probably would help relate this thing to the entropy as a functor perspective more closely. Absolutely. Yeah. So. Yeah. You can try to put a post-settle structure on this thing in my particular instance, and there's maybe some post-settle structure here, and actually get something that's functorial as well. But I don't know for sure. Okay.
While you're
Yeah.
in the chat about whether interaction information or M area mutual information is considered in the context of information theory already, and does it have an intuitive interpretation?
Yes, it's known, and it is interpreted as, it's not intuitive because it can be negative for higher partite systems other than 2. So you can look at the Wikipedia. I try to stray away from interpreting it for higher things just because you can go down a real rabbit hole that way. But I know other people really like intuitive explanations for everything. But I just think of it as sort of like a characteristic class. In fact, this is maybe the right perspective to think about Badeau and Benneken's work, where they show it's the first, mutual information is like in the first homology group. You could think of it as like a characteristic class that tells me whether or not my state is factorized. So that's my and characteristic classes, you see those in differential geometry. And I have no intuitive explanation for those things other than their characteristic classes, right? I think this might be the similar situation, but if you have an intuitive interpretation of mutual information, then go for it. It also turns out you can, however, rewrite linear combinations of mutual information in terms of things that are intuitive, like total correlation. So in my homological tools paper, I actually have a big section about how to relate those things. But yeah, to answer your question, no, no intuitive thing that I know of. There are many people who think about this though. Okay, so so examples of this are, I could take my category to be a category of sets. I get cardinality as a dimension, vector spaces just over some field K, dimensions over K. And then I could do fancy things like, I could look at a category whose objects are a vector space and an endomorphism. And I won't tell you what the morphisms are, but you can write down something very natural where these are isomorphism. Like you don't forget the information of this thing when passing to isomorphism classes. And then you get these things, like for any integer, you can make sense of n equals 0, act like dimensions. Okay, that's kind of cool. And then I can look at graded objects. I can look at graded vector spaces. I get alternating sums of dimensions. So not possibly non-negative integers. And then I can look at graded objects like this, and I get something that looks like a Lefschetz index. And that's actually very close to this mutual information deformation interpretation. Okay. So, so what is the, how much time? 5 minutes? Okay, woo! Maybe we'll just talk about the classical case. You can see the quantum one in my paper. So what is the dimension for our category of states? Well, let's just fix this thing for let's look at the subcategory of things on commutative algebras, so just measures on finite sets. And let's say that everything's finite, right? Everything's finite dimensional, so finite, yeah. Here, you can actually sort of go through some rigmarole and show that this is a nice family of dimensions. So, you know, in the Bias Fritz Linster paper, you might have seen this thing as some sort of partition function. So this also appears. You also get, okay, I can't help myself. So if I look at all finite states, so things on finite dimensional algebras, so here Q is in C. If I look at all finite states, this thing is some really cool looking sum. You get some n to the alpha trace of mu hat q to the r. And you're like, oh my God, what is all this stuff? There's some parameters q, r, and alpha that live in C. And then you start taking limits of this thing and you see Solace entropy popping out with the q derivatives. And so you see Rainy entropy in a certain limit. Yeah, and in fact, you can do a whole deformation that includes both Solace and Grady information that looks like 1 minus the dimension of, you take this parameter alpha to 0 of QR of U. This thing appears, this 1 minus appears naturally in the cohomological picture, but so I'm just claiming that this is an extremely natural thing to look at. Okay. To wrap it up, if I take the Q goes to 0 limit of this thing, what do I get? What's the Q goes to 0 limit of?
So like just n?
Yeah, so I'm going to take the convention that the 0 to the 0 is 0, but you know, any finite number to the 0 is 1. So the appropriate limit of this thing, if you think of it as like the actual limit of something holomorphic, is the number of points with omega, with mu not equal to 0. And so you can think of this integer limit as sort of, if you think of this as some sort of type of entropy, as related to entropy. And so you say, oh, I'm getting an integer. Maybe there's some vector space sitting around somewhere that categorifies entropy. And yes, there is. And I'm not going to talk about it, but I'm starting to write. I'm just putting little notes on the NLab. If you look at the GNS, page, there's a link to it. There's actually a functor, and this will tie into this, which I'll say in 2 minutes or less, actually. There's a functor from the category of states and the category, I'm just going to say modules. It's actually, with these LQ spaces, more complicated. And what this does in the classical cases, it'll take in this mu and it'll bring you to the space of functions where omega is not equal to 0. Okay. And if you do the right things, you can decorate these modules with some points and actually get some functor. You can get some isomorphism categories here. So this category of states is actually isomorphic to some category of modules with some extra data, an extra point. Okay. So that ties into this big picture here with this work with Roman and Greg, where we started thinking of things like a different way, but this category of states lives in some side of some 2 category where the morphisms are these beautiful things that appear in quantum information theory, completely positive maps. And then you get relations to matrix product states, which is another interesting thing in physics. And on the other side, you get interesting relations to, you know, representation theory, things about modules and bimodules. So, and it's all very concrete in terms of these two categorical equivalences. The infinite dimensional thing is just absolutely amazing. I know some people don't like infinite dimensions, but it really teaches you a lot, even about the finite dimensional stuff. So yeah, that's our pitch for this work. And this work was inspired by trying to figure out how there's this relationship between these matrix product states and topological field theories, and we're trying to make that rigorous. And somehow it's related to this story about entropy and through this indirect way. So yeah, I will stop it there because that was a lot of words. I don't expect anybody to understand everything. This is more of a pitch for this big picture stuff. Yeah. Okay. Can I ask what?
The audience, if they have any questions.
Oh yeah, do people have questions? Audience, virtual audience, please make me feel like not everybody was asleep. It's fine if you were. I hope it was a good nap. But, yeah, so, yeah.
Just for my imagination's sake, is there a two simplex continuation of the simplicial diagram that you were?
Yeah, you mean like this picture?
Also repeat the question.
Oh, right. So the question was, is there a two simplex continuation of this story? Is that right?
A and B, and I saw edges.
Yeah.
And points,
So-
and I wanted to go further to the
Right.
right.
If I have something on three things, you can draw pictures where you have like correlations between A, B, and C. And there's some sort of like two cells sitting in here. Yeah, I think that's this way. Yeah, and this tells you about these correlations between this cell sort of corresponds to correlations that you can only see between three variables and no less. Yeah. Actually, that's not quite right. If you fill in well, I have to think about it. But there's actually a simplicial complex associated to any measure on a finite set.
Right, you wrote
Yeah,
down the
so-
1 for 2, and I was
yeah.
just asking, because I just wanted to see the 1
Yeah.
for 3 if you knew how to write it down.
Yeah,
The plus signs and the
yeah. What you do is, I don't know if I can do it on the fly. There's a very simple formulation where I can literally look at the measure like, and there's a way to write down this one cell is this two cells this, and glue them together and make a nice picture. Yeah. Maybe I'll put something on the EnLab about that too, because I don't have that written down. Yeah. Yeah.
So Q equals 0 corresponds to measuring the dimension of the support. of the
Right.
state?
So the question was, the Q equals 0 corresponds to measuring the dimension of the support, and the answer is yes. For the finite case, yes.
Okay.
Yeah. Also, Arthur. Yeah. Yeah, that's good. Yeah.
When you talked about this isomorphism GNS, you said that there was some bells and whistles on the right-hand side. Are you assuming any minimality conditions?
Well, absolutely. Yeah. So the question was, on the right-hand side here, I decorated modules with some extra data, a distinguished point. Am I assuming any minimality conditions? The answer is yes. If you know anything about the GNS representation, you know that a state will correspond to a cyclic pointed representation. So there's some cyclicity condition here. Yeah. But you can think of pointed modules. You can think of this as a reflective subcategory of the category of pointed modules. So there's actually an adjunction. For just normal pointed things. Yeah. And this GNS thing is actually that's actually part of this correspondence between CP maps and this representation theory side. You don't know what this means. It's just bimodules.
Okay.
So a completely positive map becomes a bimodule. And an easy example of a completely positive map is just a state, it turns out. Yeah. And that reduces down to just the notion of a module over. Yeah.
So you still have this adjunction even in the case between CP maps and the arbitrary C-star algebras?
That's right. Yeah. So between arbitrary, that's right. Yeah. For W-star algebras, for C-star algebras, there's W-star algebras and have much nicer structure there's something called a Hilbert C-star bimodule, and they're very, very complicated objects in comparison to the W-star case.
So they're not,
Yeah.
they're not on the bottom right hand side of that diagram. Those are not C-star bimodules.
No, they're not C-star bimodules. The objects in these categories are all W-star algebras. A specific constraint. Yeah. So if people know what W-star algebras are, they're the non-commutative analog of measure spaces. So L infinity bounded functions on a measure space is all commutative C-star W-star algebras look like that, and you can actually reconstruct the measurable space from the algebra through this sort of spec function duality. It's, yeah.
And W-star bimodule is the directional analog of bundle over non-commutative space.
Right. Yeah. So Roman mentioned that W-star bimodule is an analog of bundle over a non-commutative space. So there's an interpretation like that as well. Yeah, with some caveats, of course. Yeah.
Okay, thank you.